This is Unit 1, Lesson 5, Functions and Relations. The objective: students will understand the aspects of a relation that define the function and find the domain and range of a function in the graph. Find values of functions for given values and solve equations for variables. There's a lot of stuff to cover in this lesson. I'm going to move kind of fast. So first, a relation is a set of ordered pairs. Now a set is a group of anything. You could have groups of numbers, groups of shapes, groups of people. It would all be a set. In this case, the set is a set of ordered pairs, just like when you graph numbers on the coordinate plane. So we have 1, 2, 2, 4, 4, 8, 8, 16. Where the first number is the x value, second number is the y value. The domain of a relation is a set of all the potential x values from the relation. In this case, 1, 2, 4, and 8. The range of a relation is all the set of y values, 2, 4, 8, and 16. It's helpful to think of a relation as a machine that does things to numbers. So if I put in a 5, those are the inputs of the domains. The machine does something to the number and comes out with another number. I could put in a 10, and it's going to do something to the number and come out with the 16.2. So we have inputs and outputs, the domain and range. That's what's important to think of. Each element of the domain is an input, and the coordinating output is a number in the range. Another way to draw that idea is like this. We could list the domain in a column and list the range in another column. And each number of the domain points to a number in the range. So that's what the machine is doing. If I put in a 5, I get a 12.8, so forth. Now a function is a subset of relations where each element in the domain only points to one number in the range. So whatever it is in the domain, I know whatever happens to the domain, whatever number goes in, I know what's coming out. So in this case, this is a function because the 1, the 2, the 3, and the 4 all point to one thing. If we put a 2 in the equation, in the machine, I know 6 is coming out. That's a function. Each number of the domain points to one number in the range. This is an example of something that's not a function. You see the 6 here can point to the 1 over 2. So if I have my machine and I put in a 6, I don't know if there's a 1 or a 2 coming out. That means it's not a function. Now sometimes the sets of ordered pairs in the function is infinite, so we can't list them because there's an infinity of numbers. So sometimes we write them as an equation. This is an equation. This is what it would look like. The f tells you that it's a function, and then after it in parentheses is an x, which means that the input for this function is the variable x. And you read it like this. It's a function of the variable x, and when you read it, you would say f of x equals 4 minus x squared. And that shows you how the inputs, the x, or the domain elements, impact and what happens to them and how they create the output, or the range element, which is f of x. So here's an example of evaluating a function. If you find f of x equals x squared plus 3x plus 5, and you need to find f of 2. Now remember, when you had f of x and now you have f of 2, so all you did was replace the x with 2, which is what you would do on the other side of the function. So f of 2 equals 2 squared plus 3 times 2 plus 5, which equals 4 plus 6 plus 5, which equals 15. So f of 2 equals 15. Now we could also potentially not just plug in numbers, we could plug in other expressions. So if I plug in f of x plus 2, I still replace all the x's with x plus 2, and it looks like that. Don't worry about the next stuff. Now we could also show functions that are infinite as graphs. In this case, you follow the thick red line. That's the line representing the function. Now whatever the x value is and the y value is on any point on that line tells you the input and output of the function. So for instance, f of 1. If I go f of 1, if I look at 1 on the x-axis and I go straight up from there, it hits the y. When I hit the line, I'm at an f of x value of about 2.5. So f of 1 is 2.5. F of negative 2, I go over to negative 2 on the x-axis and see that when I'm there, the red line at x is equal to negative 2, the red line is at f of x equals negative 2. So f of negative 2 is negative 2. F of 6, if I go over to 6 in the x-axis, that goes to 4 in the f of x-axis. So f of 6 is 4. Now if I can draw a vertical line that touches the function on more than one point of the graph, it's not a function, because that particular value for x would have two potential f of x's, and that means it's not a function. Show some examples. This is not a function because at any point between -4 and +3, if I drew a vertical line, it would touch the green line more than once. This is a function, even though I could draw a horizontal line through that touches more than once. I can't draw a vertical line, and this is the vertical line test. Only vertical lines make things not be functions. This is a function. This is also a function, even though the lines are pointy instead of curvy. This one looks like a function at first glance, but is actually not a function, because if you look at the point where x is equal to 2, there's a vertical line. And that vertical line means if I drew a vertical line at 2, then it would touch that function, that potential function, that relation, at an infinite number of points, which means it's not a function. So if there's any vertical line at all that you can draw, then it's not a function. We also have to find domains and ranges of functions. Now remember, the domain is the potential x values and the ranges are the potential y values. So you can see that the domain is anywhere between -4 and 1. And you write it like this. -4 is less than or equal to x, is less than or equal to 1, and it's less than or equal to because it's a colored in circle. And you can kind of see how x is between -4 and 1 by looking at that. The range is between 1 and 4. So it's 1 is less than or equal to x, is less than or equal to 4. Now this line goes on in infinity in both directions. So there is no limit on the domain. It could be any real number. So we say all real numbers. And I know it's funny that we're talking about real numbers instead of just numbers, but later in the year we're going to have not just real numbers, but imaginary numbers. So it's important that you say all real numbers instead of just all numbers. The range, likewise, is going to go all the way up and all the way down to infinity. So the range is also all real numbers. What about this one? Well, the domain, and you have to imagine this curving pattern repeating itself outside of this graph. The domain is still all real numbers. Anything is potential x. But the range is not infinite. Is not all real numbers, I'm sorry. It starts at -2 and goes to +2. So it's -2 is less than or equal to f of x is less than or equal to 2. So no matter what x I put in, I'm never going to get an answer of 5. All the values for f of x are going to be between -2 and 2. Now to the next part, solving for a variable. Now in these type of problems, you're going to have to rearrange an equation in order to get a variable by itself. This is helpful anytime you have to do something repeatedly in math, and you don't want to do the algebra repeatedly. You would much rather have a formula where I get isolated variable. So for this one, V equals length times width times height, which is the equation for volume of a rectangular prism. And I want to solve that for W. So I'd have to divide by L and divide by H, because that's what I would do if L and H were numbers. So V divided by LH equals LWH divided by LH, and the L and the H cancel out, which using the V over LH equals W. That's what I mean by solve for a variable. When I said solve for W, the answer should say W equals and have all the other variables on the other side of the equal sign. Here's one that's a little bit harder. Solve for A equals 1/2 H times B1 plus B2. Now B1 plus B2 is in parentheses, so that can act like a one number by itself, because you're doing B1 plus B2 first, and if those are both numbers, then it would just be a number. So first I multiply both sides by 2 to get rid of the 1/2. I have 2A equals H times B1 plus B2. And remember I said B1 plus B2, we knew if they were numbers that would be one number. So I can just divide by B1 plus B2 on both sides. Whatever that number is going to cancel out on the top and bottom fraction on the right. So I get at the end 2A divided by B1 plus B2 equals H. Now this is the hardest problem we have. We have solve for big R times R1 plus R2 equals R1 times R2, and we want to solve that for R1. Now what makes this difficult is on the left hand side of the equation, the R1 is trapped inside the parentheses. So in order to get it untrapped, I distribute the big R. So I have R times R1 plus R times R2 equals R1 times R2. Now I want to move the R1 to the right hand side so that both R1s are on the right hand side. So I do minus R1 on both sides. That gives me R, big R times R2 equals R1 times R2 minus R times R1. Now what you want to notice here is that when I have R1 multiplied by R2 and multiply the big R, that's what it would look like if I had distributed an R1 to both terms. So in order to get R1 by itself, what I have to do is factor it out, or undistribute it. So I'm working backwards. I have to do the distributive property backwards. So I know R1 is going to be outside the parentheses, and then I just write inside the parentheses what's left after I take the R1s out. So I have R1 times R2 minus R, and equals big R times R2. Now, R2 and R are both numbers, so when I subtract them, I'll get a number. So I can just divide both sides by R2 minus R, and I get big R2 divided by R2 minus big R equals R1. Okay, good luck. Here's the homework for numbers 4 through 6 on page 14. I want you to make sure you write the domain and range, even though the book does not ask that you do that. Okay, good luck, and see you next class.